Hello, this video is inverse trig functions, as well as inverse circular functions, and solving equations involving inverse trig and circular functions. So I mentioned this in class already, but I'll quickly reiterate it again. Inverse trig functions, notation, what does it mean? Arc sin x is a function that can also be written as this, where -1 is not an exponent. So if I make this the function, then this means that y equals all, and I'll underline all the angles that have sine value of x, all of them. So for example, in this case, y is the set of all the angles that have a sine value of 1/2. The first angle that has a sine of 1/2 is 30 degrees, or pi over 6. But if we go around the unit circle again and stop at the same reference angle, that's another angle that has the same sine value. And if I go around again, there's another. So there's an infinite number of angles that have this sine value of 1/2. So I can summarize all those angles by saying y equals pi over 6 plus 2 pi n. But there's also another angle, the first go around over here. In quadrant 2, there's one that also has a sine of 1/2, and that would be 5 pi over 6, or 150 degrees. So if I really want to list all the angles that have this sine value, then it's also 5 pi over 6 plus 2 pi n. Okay, so now I have a cosine value of -1/2. Where are all the angles that have that? And I'll go back to the unit circle. The first one is going to be in quadrant 2. Cosine value of 1/2 would be like right here. So that's going to be 120 degrees, or 2 pi over 3. And then there's another one down here that also has a cosine value of -1/2. So that'll be all the way around here. That one is going to be 240 degrees, or 4 pi over 3. So in this case, y is 2 pi over 3 plus 2 pi n, or 4 pi over 3 plus 2 pi n. Okay, one more example here, because in this example the family of angles behaves differently. So now we want all the angles that have a tangent value of 1. The first one in quadrant 1 is right here, 45 degrees. The tangent value is 1. There isn't one in quadrant 2 because the tangent value, if you were thinking it's 135, the tangent value is actually -1. So we have to go all the way to quadrant 3 to get the next one. So at 225, so this one is 225, or 5 pi over 4, we get a tangent value of positive 1 again. And that happens to be 180 degrees after this one. And then we won't get another one in quadrant 4, and then when we're in quadrant 1, we'll be back at 45 degrees. So in this case, we can express all of those angles as pi over 4 plus pi n. So here you see that the cycle goes pi, not 2 pi n here, and not 2 pi n over here, but pi n. Every pi n we get another angle that has a tangent value of 1. And tangent values always work like that, because this cycle of the parent function y equals tan x is pi, so that's what you would expect. Okay, inverse circular functions are different from inverse trig functions in that these have a limited range. So, as I said before, y is the family of angles that has a sine value. Family of angles that have a sine value of x. But inverse circular functions are a limited range, so we don't need all the angles that have a sine value of x in this case, because the capital A is telling us only to express or identify one angle, or an angle within a given range that has a sine value of x. Not all the angles. Not all. So what is this range? Well, for capital A arcsine, this is the range. So, visually speaking, that means here. Find all the angles that have a sine value of x within this range. Don't worry about that, don't worry about that. Don't even worry about going around the unit circle again. We don't need that. We just need all the angles within this range. It could be more than one, it could just be one. That's the range for our cosine capital A. That's the range for arctan capital A. That's the range for our cotan capital A. And then we have arc secant, arc cosecant. Since secant is related to cosine, these ranges are the same, except for the fact that because the ratio is the inverse of cosine, there is an undefined value of y at pi over 2. And then arcsine and arc cosecant are related, so they have the same range, except that the cosecant value when y is 0 has no value. In every case, the range includes every possible trig value. And that's why we have these limited ranges. Every possible sign value is included from here to here. If we included more of this unit circle, we would just get copies. For cosine, everything we need is in quadrants 1 and 2. All of this stuff are just copies of everything in quadrant 1 and 2. Okay, there's on page 770, there's a further explanation of where these ranges come from. I'm not going to go into it here. It's just too much graphing. But if you want to know why these are the ranges we use, you can look there. So let's try some examples. So capital A, arcsecant 2. So let's talk this out. I'm looking for an angle or angles that have a secant value of 2. And it's capital A, so, and this is where you need to memorize these ranges eventually. So where am I limited? I am only going to worry about these two quadrants, 1 and 2. So where is there a secant of 2? Okay, so I'm just going to draw a generic triangle here. So if our secant value of theta is 2, then that means that's hypotenuse over adjacent. So 2, 1, and rad 3. So where does this occur? This happens when we have a triangle here at 60 degrees. Okay. Over here, we do not get a secant value of 2. We would get a secant value of negative 2. And then here's the other triangle in the unit circle that has a secant value of 2, but that's not within, y is supposed to be from 0 to pi. So we don't care about that one, we don't care about anything here. So 60 degrees, or pi over 3. Arctan of negative 1. Okay, two angles in a unit circle have a tangent of negative 1. The first one is here. Second one is here. This one is 135. And the other one over here is 135 plus 180, so that's 315. Now which one do we use? Okay, this is where people sometimes forget what the range of arctan, capital A, is. The range is actually here for arctan. Cotan is this one. So we're not going to use the 135. We're using the 315. And not only that, I'm going to remind you how the range is expressed. It's expressed like this. So visually, this is the range we want to use for capital A arctan. But look at how it's expressed. It's not expressed in this direction. So I actually can't say 315. No, I can't say that. Because the range is from negative pi over 2 to pi over 2. So the only way I can express it is negative 45 degrees. Or I could express it as negative pi over 4 if I want radians. Okay, so even though 315 and negative 45 have the same reference angle, the proper way of expressing capital A arctan negative 1 is that. Okay, so now we're combining our inverse trig function with a regular one. So we're looking for the cotangent of an angle. What angle? The angle that has the cosecant of 13 over 12. Okay, so best thing to do in this case is draw the triangle first. Draw the triangle. So where is this triangle? Well, the cosecant is positive. Alright, so our cosecant range is here. And our cosecant is positive, not negative. So it's somewhere in here, right? That means our triangle is going to look like this. And since we already know that the cosecant of this angle is 13 over 12, then I can label the hypotenuse 13 and the vertical side 12, and I can label the adjacent side 5. And I need that side because I'm going to find the cotangent of theta. So that is 5 over 12. Okay, here's another combined two-step expression. Okay, so again, we need to find out where this triangle is. We're talking arc secant, and the range for arc secant is 0 to pi. So that is here. It is negative, so we're going to use this part. That's where my triangle is going to be. So the triangle is going to look like this. This is where the origin is. Okay, so they're telling us that the secant of this angle is negative rad 2. So that would mean this is rad 2 and this is 1. So we have a 45, 45, 90 triangle in quadrant 2. And I want the tangent of this angle. That would be this over this. It's not positive 1 though, it's negative 1 because remember what quadrant we're in. We're in quadrant 2. So that would be negative 1. Okay, the last subtopic of this video is evaluation of inverse relations. So basically, you're going to see an equation that has theta in it, an unknown angle, and we're just going to solve for it. But along the way, we're going to have to use inverse trig functions to find theta. Okay, so we're given the equation y equals negative 1 plus 12 cosine of 3 times theta minus 10. We're looking for values of theta, but there's a second variable here, y. So I have to tell you something about y. So I'm looking for, find the smallest values of theta for which y equals 5. So since these are circular functions, there are an infinite number of thetas where y equals 5. So I just want, find the three smallest. I just want the three smallest values of theta for which y equals 5. Okay, so I'm going to start isolating theta, and then along the way I'll input 5 for y, but I'm not going to do it at the very beginning. So isolating theta, I'm going to add 1 to both sides first. Divide by 12. Okay, and here's where the inverse trig function comes into play. I want to isolate theta, but this says cosine of this angle, which includes theta. So I got to get rid of the cosine by taking the arc cosine of both sides. So now the left will say arc cosine y plus 1 over 12, and on the right 3 of 3 times theta minus 10 degrees. Okay, I can't find the value of arc cosine y plus 1 over 12 unless I know the value of y, so now I'm going to put it in. Remember, it was 5, so this fraction becomes 1/2. Okay, that's a convenient value because we should know angle values that have a cosine of 1/2. And it's a lowercase a, okay? So we want to express all of them. So back to the unit circle. 60 degrees, as well as 300 degrees, or negative 60 degrees, have cosine values of 1/2. So on the left side, this becomes 60 plus degrees plus 360n. And I'm going to write here, or negative 60 plus 360n. So that takes care of all of those angles. Now I can continue solving for theta in both of these equations. So I'll divide by 3 on both sides, working on this equation first. Divide by 3 on both sides. And then add 10. And then over here, divide by 3 on both sides. And add 10. Okay, so these are my expressions for theta, 30 plus 120n and negative 10 plus 120n. And remember, I'm looking for the 3 smallest values of theta. Okay, lowercase n, that's going to be a whole number. So, and that includes 0, so I should try 0. If I try 0 in both of these equations, oh, sorry, I want positive values of theta. Okay, so if I plug in 0 here, or here on the right, I get a negative value, so I don't want that. If I put 0 in here, I do get a positive value of 30. So my smallest one is 30 degrees. Now I raise n to the value of 1, put it in both. Over here, when I raise it to 1, I get 110. When I put a 1 in here, I get 150. So those are my 3 smallest positive values of theta when y equals 5. Okay, so that should be enough to do your homework. We'll take questions next class period on this, and then the next batch of homework will include practice on inverse trig functions and evaluation of inverse relations.